Next, let's talk about Sylow second theorem. So 6.2, Sylow second theorem. So that's even more surprising maybe. So first let me actually define Sylow subgroups. So let's suppose that G is a finite group, and order of G is p power n times m, where m is coprime to p. So a subgroup of G of order p power n is called Sylow subgroup. So basically, that's a subgroup which has this maximal possible power of p inside G. And we already know, so by Sylow first theorem, it exists. So every group has, for every group, for every prime number, has a Sylow subgroup. But the question is, okay, maybe there are different Sylow subgroups, maybe they have different types. And second theorem tells you that actually that's not the case. They are all isomorphic. So basically we have a group, there is exactly one for every prime number type of subgroup it might have. Like suppose p equal to 2. Then every subgroup, every group whose order is divisible by p squared and not by p cubed has a subgroup either of type z over pz times z over pz or z over pz squared, and that cannot happen simultaneously, so only one of those. So let me formulate a stronger theorem, but in particular it will imply that. So theorem is as follows. So suppose, so if S is a subgroup of G, and order of G, so order of G is this p power n times m, where p and m are coprime, and order of S is p power k, then S Okay, so let me now formulate second Sylow theorem, and I formulate slightly more general statement, and we will prove it. So theorem is as follows. So let's suppose that S is a subgroup of G, order of S is p power k, and P is a p Sylow subgroup of G. So we have some p subgroup, so some subgroup of order p power k, and we have p Sylow subgroup, which has this maximal possible power. Then there exists G inside G such that if you take S, it will be contained inside the group conjugate to G, to P, sorry. So let me explain it in a slightly different way. So you have your group, and it has a Sylow subgroup. So you can conjugate it and get another subgroup of the same type, of the same size, and you will get another Sylow subgroup. So basically you have tons of subgroups which are conjugated between each other, Sylow subgroups. A priori it might happen that there are some other Sylow subgroups not conjugate to these ones. But then what the theorem tells you is that for every group of order p power k, there exists some conjugate to our p Sylow subgroup which contains it. So in particular, if P prime is another Sylow subgroup for the same prime, then we know that there exists G in G such that P prime is contained inside G, PG inverse, but they have the same size, but the orders are the same because it's just this maximal power of P which is dividing the order of G. So this means that P prime is equal to GP G inverse, and so all Sylow subgroups of G are conjugate to each other. So that's an interesting statement. So this theorem tells you that firstly, all Sylow subgroups are conjugate to each other, and secondly, every P subgroup is contained inside one of those. So that's a very strong statement. And maybe also let me add, in particular all Sylow subgroups are isomorphic. So, because if two subgroups are conjugates, then it means that conjugation is an isomorphism between them. So basically, there is just one type of Sylow subgroups for every P. So before proving it, proof is actually very simple, but let me look at some example. So example might be, let's take symmetries of tetrahedron, which we know very well is isomorphic to S4. So we have a tetrahedron and it has symmetries, and we know that this group has order. So order of S4 is 24, which is 2 cubed times 3. So starting from today's class, for every time you see a group, you just immediately decompose its order into primes and see what powers you have. So let me use NP will be number of Sylow P groups. So I have Sylow 3 groups and Sylow 8 groups, and I need to understand who they are. So Sylow 3 groups must have order 3. So these are the same as elements of order 3. And we know very well who they are, so they are 3 cycles. So they're just all elements of order 3, so these are just 3 cycles. From the point of view of tetrahedron, these are just rotations around points, around vertices. And notice that they are all conjugate. So we know that they are all conjugate because we know that in any symmetric group, the conjugacy type of an element is just its cyclic structure. But we also know it from Sylow theorem because we know that all these groups should be conjugate in G, so it means that we kind of have 2 different ways to see why all 3 cycles are conjugate to each other. Okay, what about Sylow 8 subgroups? So 2 cube is 8, and so we expect that there should be a subgroup of S4 of order 8. And that's slightly less trivial, so let's try to understand that. Okay, so Sylow 8 subgroups. So Sylow 8 subgroups. So let's think about them. So what do we know about S4? So one thing we know is that it has this Klein subgroup of order 4. So the subgroup consists, I remind you, of this identity 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3 elements. So why I mention that? Because it has 2 properties. Firstly, it's normal, and it has order 4. So if H . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . 4 . is a Sylow subgroup, then we know there exists G such that GHG inverse contains V4. So just because this is a theorem which I mentioned before, but also of course this is equivalent to saying that H contains G inverse V4G, but V4 is normal. Remember, this one is normal, so this is just V4. So we get that all Sylow subgroups contain this V4 group. So in S4, all Sylow 8 subgroups contain this group. And so now we can try to understand who they are. So if you want to find a group of order 8 which contains V4, of course you just need to add one element, and we can do that. So let's just add some element. And again, I mean, which element? So theoretically, we definitely should not take a 3 cycle, because then the group will have order divisible by 3, and we are looking at a group of order 8. But we can either take a transposition, or we can take a 4 cycle. And we should get the same thing, because we know that every Sylow subgroup, every transposition is contained in some Sylow subgroup. Every 4 cycle is contained in some Sylow subgroup. And they're all conjugate. So what should happen is that basically each of them contains both transposition and 4 cycle. And that's indeed what happens. So if you just take identity 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3, and you just add another 2 cycles, say 1, 2. So then multiplying, you get that it has also 3, 4. And then multiplying on, so that's already a subgroup, that's a subgroup, so we can multiply 1, 2 on 1, 3, 2, 4, and get, so that sends 1, 2, 3, 2, 2, 4, 3, 2, 2, 4, 2, 1, and that's a 4 cycle, so 1, 3, 2, 4, then it should have the inverse, which is another 4 cycle, 1, 4, 2, 3, and that's actually it. So there are 8 elements, and you can check it's a subgroup. So how to see it geometrically? So as I already promoted last class, so if you want to find a subgroup of some order, it's very nice to look at group actions. So why don't we find a group action where such subgroup is a stabilizer? So we want a subgroup order 8 to be a stabilizer of a point, so it means we want a transitive action on a set with 3 elements. So to find a subgroup of order 8, we need an action on a set with 3 elements. And of course, such an action can have, orbits of different types, but we need transitive, meaning with 1 orbit, transitive action. So, and then we will find this group. We know we will find this one, but trying to do it in different ways. And remember, so we already had a subgroup, an action on 3 elements. You just take this middle diagonals. And when we get this subgroup, so there are 3 such diagonals, and to get the subgroup, of course, you just take, so you want this to be a stabilizer, and so you want a diagonal which is stabilized under 1, 2, and 3, 4, so it will be this one. So if you just take action on 3 elements, which are these 3 kind of segments connecting midpoints of opposite faces, and you look at stabilizer of this one, so this is a stabilizer. So there is this action on 3, let me call them L1, L2, L3, and these are the 3 lines, and this is stabilizer of L1. So in some sense, you don't need to do all this work. So you can just say, okay, we have an action of our group on this 3 lines, and then the stabilizer is our group. And we know that this will be exactly 3 Sylow subgroups because we know they are all conjugate. On the other hand, if I have an action on 3 elements which is transitive, then conjugate of stabilizer of one point will be stabilizer of another point. And so we know that there will be 3 Sylow subgroups corresponding to these lines. So there are 3 Sylow, 2 Sylow subgroups. Okay, so that's the picture. So next I want to prove Sylow's second theorem, and then give some more examples of Sylow subgroups. Okay, so proof. So let's recall what we have. So we have group order G, group G, and we have, so P is a P Sylow subgroup. And we have some subgroup S inside G, and S is just some P subgroup. Okay, so we need to show that S is contained inside a subgroup conjugate to P. How to do that? So here is the idea. So let's look at cosets. So G over P is a set of left cosets. So, and I can denote them G1, P, G2, P, GKP. And I know that this K, of course, will be exactly the index. And in particular, since it's a Sylow subgroup, I know that K is coprime to P. Perfect. So now I have this set and I want to act on it. So how to act on it? On a set of cosets, there is this nice action. You can just take any element of G and multiply. So when you multiply from the left, a coset is going to a coset, and sometimes the same, sometimes different, and that's a very interesting action. But what we'll do, we will multiply not on elements of G, but just on elements of S. So S acts on this set by multiplication. It's called left multiplication. Left multiplication. So if you wish, I mean, in sort of informal way, you can think that you have some element S, and then what you do, you just take kind of K elements G1P, G2P, and so on GKP, and you just multiply each of them by S, and you have, again, so conjugacy classes will go to conjugacy classes. That's their kind of basic property, and so you have a permutation. So that's that permutation. So this S permutes conjugacy classes. So that's the idea. It's a little non-trivial, so of course it's easy to show, but this idea that actually if you just think how all elements S, when you act, how they permute classes, that you get something non-trivial, it's not very obvious. But actually it is non-trivial. But let's see what we have. So S is a P group. So since order of S is some power of P, then all orbits have either length 1 or length divisible by P. Actually, not just that, but power of P. So, I mean, length of orbits can be 1, P squared, up to Pk. So either 1 or something divisible by P. But then again, if you just use the fact that we are acting on a set which is not divisible by P, and orbits have either size 1 or divisible by P, as before we conclude, so number of fixed points is congruent to -1 mod P. So if you add 1 to it, you get, sorry, what I'm saying, no, its number of fixed points is number of fixed points is congruent to P, is divisible by P. Sorry, what I'm saying. So you have a set whose size is not divisible by P. And you know that these orbits all are divisible by P. So then there exists an orbit of size 1. So then this action has a fixed point. Action has a fixed point. So there exists a coset which is fixed. So there exists G such that for every element, so G in G, every element S in S, we have, if you take S, multiply on G, and multiply on P, that's just the same as GP. And of course, in particular, we have identity here, so it means SG is inside GP, but that means that S is inside GP G inverse, but that's true for every element S, so it means that S is inside GP G inverse, and we are done. So in this way we prove the Sylow second theorem. So you see it's rather non-trivial and very rich and quite incredible statement. So why it's so useful? I mean, other than applications we'll see later, but just intuitively, it tells you that if you want to understand what are Sylow subgroups of your group, you just need to find one, and then all of them are of the same type. And not only isomorphic, but actually kind of conjugate, so it means they are isomorphic and look similarly inside your group, so they are kind of all looking the same. So we have already looked at S4 case, and in general we can analyze Sn case, and there is an exercise in homework. So let's look at projective groups and projective geometry, because that's also interesting. Okay, so we start with GL2 of Fp. So let's recall the size of this group, so the G. So I already made this argument, but just again, so the order of G is computed as follows. So you know that to understand an element there, you just need to take a standard basis and take some basis and just move the first vector here, the second here. And you can think of this one as being, I don't know, 0, 1, 1, 0, and the second one is just arbitrary. You're trying to do that. And then you just need to first choose where the first vector go, and this can be any point except 0. And then you need to understand where the second vector go, and this can be any point except the line which we have already looked at. It's p squared minus p. So order of G equals to p times p squared minus 1 times p minus 1, and in particular it means that the power of p inside the order of G is just 1. So we know that G has a P Sylow subgroup of size P. And so it's cyclic. So cyclic. So how to find one? Okay, so there are different ways. Probably, sorry, I did something strange. No, p squared minus 1, yeah. Yeah, so how to find one? So the simplest way is just to present it. So take matrices, so consider a subgroup P consisting of matrices of type 1, x, 1, 0. Inside G. So this matrix is always invertible, so for any x inside Fp. And you see that the order of this subgroup is P and actually just isomorphic to Fp. And the reason is because if you just take an isomorphism which sends I will do the other direction, so x goes to 1, 1, 0, x, and y goes to 1, y, 1, 0, 1, then xy will go to the product, but the product here is just the same as, so if you multiply you get 1, 0, 1, x plus y. And this means that sorry, what I meant is x plus y goes to this matrix, which is exactly the product. So we have a homomorphism from Fp as additive subgroup to P. So Fp's additive subgroup is of course cyclic. So that's one example, and that's interesting. So what if we take GL3 of Fp? So again, to compute the order, we just notice that so now we have three-dimensional vector space, and we need to choose three vectors which form a basis. First we take any vector which is not 0, then we take any vector which is not on this first line, and then we take any vector which is not in the plane we just constructed it. And so this equals to P from here, P squared from there, so it's P cubed times M, where M and P are co-prime. So we are looking at P cubed Sylow subgroup. So what is a P cubed subgroup? And the answer is just do the similar thing. So you can take P being this matrices 1, 1, 1, 0, 0, 0, x, y, z. And if you just multiply these two matrices of this type, so if you just multiply them, x1, y1, so firstly they are all, so the number of such matrices definitely is P cube. So the order of P is indeed P cube. And we need to check that if you multiply them, you get another matrix of this type, and that's of course immediate, because if you just multiply it, then you will get 1, 0, 0, 1, 1, 0, and then x1 plus x2, z1 plus z2, and finally something more complicated, so it will be y2 plus y1 plus x1 z2 in the top corner. So you see that basically everything is super simple except this term. So this group is not abelian. So P is firstly we see it's a subgroup, right? So you multiply two elements, you get an element there. So P is a subgroup, indeed a subgroup of G, and we know that it is Sylow. And also we can understand, so it's easy to see from here that you have a homomorphism from P to z over pz times z over pz when you just send the matrix 1 x y z 1 1 0 0 0, and you just send it to x comma z pair. So they are added when we multiply matrices, so it's a homomorphism that's clearly surjective. So that's surjective. And if you have a kernel, so kernel so this is f, and kernel of f, it's again isomorphic to z over pz, and these are just matrices of type 1, 0, y, 0, 1, 1, 0, 0, 0, and if you multiply them, you easily see that you also get that this is isomorphic, so if you send it to y, that's an isomorphism. So kind of kernel is z over pz, and there is a image as z over pz times z over pz, but P is not abelian. So P is some complicated group which is not abelian but kind of sits in between. So that's kind of an interesting case, and it's called a non-trivial extension, and in general the name of this subgroup is called Heisenberg group, and that's really useful in quantum mechanics. And you might ask how this kind of finite fields has something to do with quantum mechanics, but actually there is a very deep relation. So, okay, so this is an example of Sylow subgroup, and again, we know all subgroups are conjugate to this one. So there is a matrix, so that you take X, anything like that, X inverse, and you get another Sylow subgroup. Okay, so here we end the story about second Sylow subgroup, and next time we talk about Sylow's third subgroup theorem, which is the most complicated.